This is episode 10 in the Problems in Real Analysis series. This should be the last episode for a while because I want to focus on other things. Particularly, I want to focus on research. But I also want to do different things with the channel. I want to wrap up the not the measure theory, but the interviews with grad students, which should be wrapping up here really quickly. I also want to start doing the measure theory review series, which here are the notes, more or less. I've got 5 chapters. I'm in the 6th one right now. There's going to be 10 total. So once those are all recorded, I'll upload those to the YouTube channel for people to watch. And then I'll probably do different types of videos where I talk about not specific math-related stuff, but grad student stuff in general, because it is supposed to be a grad student channel, not so much a math channel. But anyway, let's do the last 3 problems for at least the time period. I probably will return to this series in the future, but let's do episode 10 and then worry about that later. Okay, so the first problem here is we have a family of non-empty Lebesgue measurable sets in the unit interval. So these are all subsets of the unit interval. They're all non-empty, and they're all Lebesgue measurable. We assume that the limit, as n tends toward infinity, of the measure of each en is equal to 1. So they're getting larger in some sense, in the sense of measure, they're getting larger. And we want to show that for any epsilon between 0 and 1, so that's a strict inequality on both ends, there exists a subsequence of sets. So this is the subsequence that we're choosing. I understand I'm using the subset symbol here kind of inappropriately, but that was just the notation that I adopted when I was doing these problems. I know I'm talking about a subsequence here. So there exists a subsequence such that the measure of the intersection of those chosen sets is strictly bigger than epsilon. Okay. So how do we approach this problem? One of the tricks that we use is that because the sets En are, it may not be obvious at the beginning, but they're not as easy to work with as opposed to the complements of those sets. So instead of looking at the sets En, we're going to look at the complements of En, which when I say complement, I'm really meaning the relative complement, meaning take the unit interval and get rid of En and call that En complement. So if the limit of measure of En goes to 1, or is equal to 1, then the limit of the measure of the En complements must go to 0, which should make sense because we're in the unit interval. And then we want to choose a very specific sequence of integers nk such that the measure of enk complement is strictly less than 1 minus epsilon over 2 to the k. And this seems kind of strange. You don't really see where this is coming from. But we can do this because we can think of this as an epsilon by another name. So I really should have started with let epsilon be given because that's how all of these analysis proofs start with, right? You have let epsilon be given and then choose the thing that depends upon epsilon. So epsilon is given to us, and we choose this integer nk such that the measure of this set is less than this number, and we know such enk complement exists because the limit tends to 0 up here. So if it tends to 0, eventually it has to be below this threshold at some point. So that's how we're going to choose those ENKs, or ENK complements. And then, if we look at the union of those ENK complements, and then take the Lebesgue measure of it, we can apply countable subadditivity and get that this measure is less than or equal to the sum of measures, ENK complement, but the measure of this guy is bounded above by 1 minus epsilon over 2 to the k. And then the 1 minus epsilon can be carried out of the sum, and then the sum of 1 over 2 to the k, where k goes from 1 to infinity, gives me 1. In which case I'll get 1 minus epsilon times 1, which is where this 1 minus epsilon is. Although I think I misspoke there. That sum should be less than 1, but it's fine. We can just... No, it should be... No, it's right. What I've written is correct. Never mind. Okay, so Now we know how big the union of E and K complement is. So now let's look at the intersection of E and Ks. So, because that's what the original problem was about, the intersection of E and Ks. So if you take the measure of the intersection of E and Ks, we know that the measure of this set has to be 1 minus the measure of the union of the complements. So, because, how do I describe this? I mean, if you understand set theory pretty well, you can see the argument here. But it's more or less like, should I say applying De Morgan's law? Because it kind of is. I think it should be fairly straightforward. I'm struggling to find the words with it, but if you're intersecting all these E and Ks and you're wanting to measure that small set, then one way of looking at it is like, okay, take the measure of the full interval and then just remove all the stuff that was outside of the set. And that's how we end up getting this guy. But this guy is bounded above by 1 minus epsilon, right? Yes. It's bounded above by 1 minus epsilon, which means that this guy is bounded, the whole thing, 1 minus this, is bounded below by 1 minus epsilon. And then if you push the negative through, simplify your algebra, you'll get your epsilon in the end. And the theorem, or not the theorem, but the problem is done. So it's a very short problem with some very powerful ideas. And if you have a very, in the beginning you read this and you're like, I'm not really sure how to proceed with this. But when you see the solution, there's a lot of really smart ideas in this very short proof, which is one of the reasons why I like this problem so much. And then what I've written here at the bottom, were kind of like my notes when I was going back over this and studying for my test, just to get the main ideas. But anyway, that's this problem. I think this was a homework problem from another real analysis class that I found from a friend. Very interesting problem. Okay, so this problem was on my qualifying exam. I've talked about this problem before, so I'm not going to talk about it anymore. But I will show the general idea of how it's proved, or at least to the best of my ability. You have a continuous function f from Rn to Rm, so between two Euclidean spaces, and everything here is nice. It's the normal Euclidean distance. It induces the usual topology that we're familiar with. Everything here is nice. You let U be some open set in Rn. And we want to prove that the image of U under F is a Borel set in Rm. Okay, so there's a couple different ways you can approach this problem, and this was the way that I approached it. And what I wanted to do was take the space Rn and split it up into cubes. So we have the unit interval n, which is just the Cartesian product, 0, 1, cross 0, 1, cross 0, 1. You have n terms. So you have a cube. Think of this like, think of Rn as like R2, for example. Then you have a square here. And then we define Zn to be the set of all lattice points in Rn. So lattice points means that each of these terms in the ordered pair is an integer. And then I define QV to be equal to Q plus V, where V is a lattice point. So I'm just taking Q and I'm translating it all over the plane, if you think of it in R2. And then we have a couple different cases. So the first case is what happens if U intersected with QV is empty, which means that the cube doesn't touch U. Well, in that case, it's not very interesting, because if you pass the empty set inside the continuous function f, you get the empty set, which is a Borel set. You probably don't even really need to write this line, but I wrote it anyway because I wanted to exhaust all possible situations. And then you have the case where U intersect QV is equal to QV, which means that the cube is inside of U. So if QV is inside of U and you pass it through a continuous function, continuous functions map compact sets to compact sets, which means that FQV is compact and compact sets, leave that in. Compact sets are Borel sets, so we know that FQV is a Borel set. And then we have the interesting case where U intersected with QV is non-empty, but QV get rid of U is also non-empty, which means that U passes through QV, but it's not like a subset of it. And one way that I did it was I considered the set of all X values that are inside of the intersection, such that the Euclidean distance between X and U complement, so we're outside of U, is greater than or equal to 1 over n. So you get this like compact subset of this intersection, and we know that compact subsets will map to compact sets under the continuous function. So that's kind of what I've written here. And so if we have a compact set, it's definitely a Borel set. So this set is definitely Borel under the continuous map. And if you take the union of those sets, so I denoted this as Sn for simplicity. If we take the union of Fsn, then we can pull the F out, so to speak, and get F of U in Sn. And this indeed gives us a Borel set, because this is a Borel set. If you union Borel sets, you get Borel sets. And this was what I was really interested in, because this tells me that the original set here, U intersect QV, for this case, is also a Borel set. Because as n tends toward infinity, this guy tends toward 0, so that compact set that's inside this guy increases up to the original set that we wanted, or at least in this case. So we have Borel sets in all three cases. And the only case I really didn't write here is what happens if U is a subset of a cube. So what I'm saying is that we split up, because I actually wrote this up and then I realized at the end that I didn't cover all cases. But what I'm saying is that if you split up Rn into cubes, and it just so happens that the open set U is pretty small, meaning that it's completely contained within some cube, then all you have to do is take that one cube that it was a subset of and split it into like dyadic cubes, for example. It doesn't have to be a dyadic, but you split up the cube in such a way where you end up getting these three original cases again, and then you just repeat the same argument. And then in the very end, all you say, okay, so for all three cases, you had Borel sets, you union all these Borel sets together, you still get a Borel set. So F of U is a Borel set in Rm. This problem was completely written by me, which means it scares me because I don't trust my math abilities anymore. But I'm pretty sure I didn't say anything horrendous there. Okay, and so this is the last problem. We have two sequences of functions. So Fn is a sequence of measurable functions, Borel measurable, and Gn is a sequence of Borel measurable functions. Both sequences are defined on the Udent interval, and they are non-negative, finite non-negative functions. And what do we assume? We assume that Fn converges in measure to 0, and that the integral of Gn over the interval 0, 1 is strictly less than 1 for every single n. And then we want to prove that Gn times Fn, so we're defining a new sequence of functions, Gn Fn converges in measure to 0. I believe that this was a homework problem given to us, and I was, so I believe this problem was given to us as a homework problem, and I worked with the instructor to try and solve it a certain way that I presented. I think I presented this to the class, and I did it differently than the way I'm about to show you here because I found someone else's solution and I liked it more. So I'm going to show their solution. Whoever wrote this up, props to them. So yeah, I wrote here, this is an alternative proof to the one provided earlier, because this problem shows up twice in my stack of homework problems to do. Anyway, let's do the problem. Let epsilon be given. Yes, finally, we say the mantra, epsilon is given. We want to show that this converges in measure to 0, so we're going to apply the definition. So we want to show that this set, has arbitrarily small measures. So we write it up the way the definition tells us. And I believe we can split this set into two pieces. So the first piece says, all right, absolute value fn_gn is bigger than epsilon. So that's what this set is. But we require the additional assumption that the modulus of fn is bounded below by epsilon squared. And so if we do that, the set only gets smaller. And what do we do with all the points that did not show up here? Well, we put them over here. So all we're saying is fn in absolute value is less than or equal to epsilon squared. So we've taken our first set here and we split it up into two different sets. Okay. And now we want some inequalities. So apparently, let's start with this one. So if fn in absolute value is less than or equal to epsilon squared, then we can do a substitution here and pull it out. So we know that epsilon squared modulus gn is bigger than epsilon. Okay, so this kind of, can I really say this? I'm pretty sure I can. I just want to make sure. I'm curious if this is equal to this or if I made a mistake. Let me think for a second. No, it should be fine. It should be fine. But this guy over here says, okay, just drop this assumption. So if you drop this assumption to the right of my finger, then the set can only get bigger because you're asking for less. So the set only gets bigger, so that means we get less than or equal to here. And then in the next line, we say, okay, well, divide both sides by epsilon squared here, so we get absolute value gn is bigger than 1 over epsilon. And this set, we can apply Chebyshev's inequality. So this set is bounded above by 1 over this number, which just gives us epsilon right here. And we take this epsilon and multiply it by the integral of gn in absolute value over the interval. And this guy, this is just Chebyshev's inequality. And this integral, by assumption, was less than 1, which means that this guy is less than epsilon times 1. So our next line becomes this. So this set just moves down here, and we have an upper bound for this guy, which is just epsilon, which goes right here. And then what can we say about this set? Apparently, I'm saying that it is less than epsilon squared by assumption, which is true because we said fn converges in measure to 0, and epsilon squared is just epsilon by another name, or a different type of epsilon, if you will. So this is true by assumption. So what do we have? We have an epsilon squared here plus epsilon here, which means so for sufficiently big N, the measure of this set is less than 2 times epsilon, which, is that true? I guess it's true if epsilon is small enough, which is really what we want. So I really should be careful here because I've written epsilon squared here and epsilon here, but I really want this to be less than epsilon. But if epsilon is between 0 and 1, then epsilon squared is going to be less than epsilon. So it's not true for every single epsilon, but it is true for small epsilon. So then we'll have this, which means that we have convergence in measure to 0, more or less. It's kind of nasty to have epsilon here and 2 epsilon here, but I do know that if epsilon gets really, really tiny, then everything should be fine. I just don't like the 2 there, but I think that's just me being a slave to definitions. Anyway, that was the third problem in the line of episodes of Real Analysis. I hope you found this informative. If there's any mistakes here that I missed, or if I made some egregious mistake, I welcome you to correct it. Make a comment below if you have thoughts, because I know I'm prone to making mistakes. So thank you for watching these videos. I hope you found them informative, and I'll see you in the next one.